hello everyone, welcome OpenFoamers to this video discussion of CHT multi-region foam. So, in the last video, we found out that, our simulation wasn't exactly representing reality in the sense that, yes, the Rayleigh number did not match up with the Nosop number. So, all of this stuff, I have classified them into this thing called coarse mesh sphere oil in GitHub, and this was at least one iteration of a last working case of OpenFoam. So in this I have put in the results which I have shown you before. You see the heat transfer coefficient. Yes, it does match well with the two methods of heat transfer coefficient calculation does work well, and showing you also that it doesn't match the Nosop and the Rayleigh number. Of course, you can use temperature as the basis of comparison, but yeah. So what's going on with this big mismatch? Is it turbulence or is it some other case? Because we realize that even in the laminar regime, there's a big mismatch between the Nosop and the Rayleigh number for the OpenFoam case as compared to, let's say, the case of correlation. So where experimental data was used. So what could be going wrong? Well, the other thing I wanted to talk about was using mesh. The other potential problem could be that it was a mesh problem, meaning to say that the mesh is too coarse for us to use. So there was a way to actually talk about mesh refining. So I tried using a level 4 refinement in Snappy Hex Mesh. What is the level 4 refinement? Well, let's go through. Okay, so last I copied this coarse mesh sphere oil case into here. So that was the last few videos we were talking about, the case that actually worked. So I started with by copying all of this into this thing called the experimental case. This is where I kind of do all my experiments behind the scenes to gather knowledge, and then after that come and share. So what I did was I go to System, Snappy Hex Mesh Dictionary, and what I do is over here I have this explicit feature edge refinement. I increase it to level 4, and of course surface-based refinement, especially for the sphere. The maximum and minimum, I increase the refinement to level 4, meaning to say it will refine from level 2 to level 4, it will refine like 16 times as much. There'll be a lot of a finer mesh. So what happened? What happened was this. I can go to ParaView to open a screenshot. Open the case on what it looks like. But anyway, the screenshot of ParaView I have already is in this case. We can see that the sphere is a lot nicer and the mesh is a lot finer near the boundary, which is, at least in theory, what we want. We want smaller meshes at the boundary, right? Okay, so that's what we want to have. Okay, however, this is the kind of the first knee-jerk instinct we will go to refine the mesh. However, that's not really what we want, because as you can as I have tested later, it causes a lot of problem. Okay, so what kind of problems am I talking about? Okay, I'll just wait for ParaView to open. So now ParaView is open, and I'd like to go and show you the fine mesh sphere, or at least the experimental case. And this is where I have named it, calling it the troubleshoot.foam, for obvious reasons that I've been going through lots of troubleshooting, and it's not been yielding very positive results. But anyway, it's a very good learning experience, so it is good to take a look at what's going on. So this is a surface, and of course you can take a look at the wireframe and you will see that the sphere is very nicely colored. Okay, the sphere is very nice and smooth, at least this time according to the mesh. If you want to take a look at the mesh more finely, I can add a slice filter, and that will do. And what I can do is use a solid color for the slice, and I'll use the surface with edges, and that will give you the slice filter. Of course, this is the mesh that we actually end up with using just a very brute force refinement procedure. And then we see all these meshes having a very strange-ish shape near the boundary. And remember, okay, just keep this in mind that the sphere is supposed to be 500 or 500 Kelvin, and the fluid is supposed to be 300 Kelvin. Okay, so when I started this, it gave me a very funny, very funny, what do you call it? A very funny result. Okay, so what I do after meshing, I have a log CHT multi-region form here. I'll show you what the results are like. Okay. Okay, there were several steps I went through this, but after several iterations, you see the temperature actually jumping to about -700, which is non-physical, and of course the max temperature is 1700 Kelvin. Again, this is not a physical result. So there's obviously, you know, something going pretty wrong with this situation. Now my first gut instinct was, okay, was this you know, because the solver could not resolve, you know, turbulence. So I reduced the temperature to 400 Kelvin instead of 500 Kelvin, where the Rayleigh number is, you know, you'll not be in the turbulent regime. How do I know that? So if we were to look at the Excel sheet I was talking about in the previous videos, we will see that, okay, there's a certain number of Rayleigh numbers that are above 3 times 10 to the 8. And we see the sweet spot temperature for this is about 417 Kelvin. So remember, we were having a Rayleigh number that changed with temperature, and all the ones that were above 3 times 10 to the 8 are highlighted, and this is the threshold one, and the temperature of the sphere then was actually about 415 Kelvin. So logically speaking, anything 400 Kelvin and below should be a laminar simulation. So I should not be dealing with turbulence for all these Rayleigh numbers, right? 3 times 10 to the 8 and below. So that's why I changed it to 400 Kelvin, and nevertheless it's still giving me this same funny result where the temperature fields are oscillating, diverging in this sense. So oscillating meaning to say, okay, the max minimum temperature is below 0, or even below, you know, 300 something, which as is what it should be, and so yeah, it's below 300 and something. I mean, below our start temperature, and yeah, in the oil region, it's kind of weird. All this this minimum and maximum temperature. So as you can see here, the min-max temperature here started to oscillate. So our oil temperature, the maximum should be about 400, which is physical, but the minimum should not be lower than 300, because that means there's some cooling effect. So if you take a look at all this, you see that the oscillations are starting from a few time steps before. So something is obviously wrong with this simulation, because we see some minimum temperature, and there's some cooling, so-called simulated cooling of the oil. So something is really wrong with this. So the first thing, was it because I was thinking, was it because of the, you know, was it because of the convergence problem? Meaning to say that, Okay, was it such that the relaxation factors were an issue? That means the FV solution in the oil, was it an issue? So, okay, these were my notes. So this is where I change all the, this experimental case is where I change all the FV solution related stuff. So what did I do with the fvSolutions? I made the tolerances really strict. Instead of 1 times 10 to the 5, I changed it all to 1 times 10 to the 9. So I make it very, very, very strict in terms of temperature. In addition, for the pimple controls, I have set all the tolerance to 1 times 10 to the 9. Alright. And I have also set the relaxation factors for all these fields to be 0.001, meaning to say that the simulation should move on very slowly, and at least the residuals should not be causing a problem. Nevertheless, the residuals weren't exactly the problem in this case. Okay, because we see that for this very non-physical result of let's say you start to have cooling of the oil, so to speak, where the temperature drops below 300 degrees. You see the residuals, the final residuals are below 1 times 10 to the 9 for all of them. The px, py, pz, ux, uy, uz, and h. So looks like the residuals in the fvSolution dictionary were not the problem. So that is what I did. Could it be a convergence issue? I tried reducing all the factors to relaxation factors and the tolerances to very small values. It did not work. Was it a time step issue? I tried reducing that too, and it did not work. And what I had to conclude was that, okay, from this document here, so this is by WolfDynamics. They have some good PowerPoint presentations there. Usually what they say, okay, this one particularly was not from WolfDynamics, but rather from the CFD Direct OpenFoam user guide, openfoam.org. Okay, where is it? Yeah, it was from this one where we had mesh. Yes, okay, this is where it is. Generally uncorrected, and these are fvSchemes. I was messing around with fvSchemes, but okay, what I want to highlight is this: at non-orthogonality above 80 degrees, convergence is generally very hard to achieve. Now, what is all this orthogonality about? For this, we need to actually understand what how this OpenFoam actually solves all the equations, and that's related to Gauss Theorem. Okay, so the in-depth understanding I'll explain a little later, but we can, speculate that probably when we do our mesh, we look at the shape of the mesh near the boundary. We see it's very highly irregular, and that can actually mess up the solver. Okay, that can actually mess up the solver. All right, and what does the solver do? For that we need to study the fvSchemes a little more and take a look into Gauss Theorem. Okay, so this is what Gauss Theorem is about. Let's see. So you go to the OpenFoam user guide. Okay, you go to the OpenFoam user guide. We will see this introduction of schemes and what they are about. This is pertaining to the fvSchemes especially. So this gives us an in-depth look into how OpenFoam usually solves all of these equations, these CFD equations, and why it gives us insight into why a poorly designed mesh, such as the one I just shown you, will cause instability problems, such as what was going on. Okay, and a very good resource is, of course, to take a look at this WolfDynamics PowerPoint, which I will want to put inside the video description. So yeah, let's just take a step back and take a look at the theorem being used. Okay, so let's say we have this what do you call that? So let's say you have this equation you're starting with, where you have del by del t of rho phi, and which is the unsteady state solution. This is the unsteady term. This is an accumulation term. And then the second term talks about convection. Okay, convection is basically, yeah, convection is basically you know, the fluid will carry some quantity in or out, and that quantity is over here called phi. It may sound very abstract now, but let's just say phi is a representative for quantities such as, for example, enthalpy. So let's say the change in enthalpy in this unit volume will depend on the convection of enthalpy in and out of this control volume, and then you'll have some diffusion term, which is probably, you know, talking about, you know, there's some conduction term, and source as well. Source meaning, say, is the heat generation within this body, within this control volume. So how does OpenFoam deal with this partial differential equation? So what it does is, OpenFoam does this thing called the finite volume method. It separates out the entirety of this space. Okay, let me use paint. It separates out, let's say you have a domain here, you have, okay, let's say the box I was talking about. Okay, and then you have the sphere in the center. Okay, and what OpenFoam does is to chop this up into many small little blocks, and they're called hexahedral blocks. Okay, these are hexahedral blocks. What is hexahedral? These are six-sided, basically. So for example, a cube, right? A cube is six-sided. All right, a cube is six-sided, and that's why we call it hexahedral. So if there are any kind of a six-sided object, six-sided 3D volume, they're called hexahedrals. So a hexahedral shape. And when we talk about snappy hex mesh, so snappy hex mesh, hex means six, and it means that it will generate a mesh with six-sided volumes. So we'll have cubes or distorted cubes. So OpenFoam usually has distorted cubes. You'll have distorted cubes, which are the hexahedrons we're talking about, to make our mesh. Okay, I open two paraviews. Okay, yeah. So this is the slice view of those hexahedrons, and if we have a 2D thing to cut everything up, so this is what the finite volumes will look like. Okay, that's why we use things like block mesh and everything to generate the mesh. Another example is this. Of course, depending on what the settings are you use for snappy hex mesh, you will generate slightly different meshes, but more or less it will look something like that. Okay, so this is what we are coming up with. We have this very weird shape over here, again probably due to some of the quirkiness of the code that makes it do that. Okay, so what it does is, okay, OpenFoam, the long and short of it, OpenFoam cuts this big volume up into small volumes. And the thing about this, how does OpenFoam calculate these volume integrals. It is used with something called the Gauss Theorem. Okay, and Gauss, okay, I think I should open in a new tab. Okay, this is Gauss Theorem. Okay, so what is this actually? Well, let's say we have this integral of some divergence with respect to volume. So okay, there are several terms to calculate here. One is this integral. One are all these integrals with some divergence in there. And what Gauss theorem does, and basically for OpenFoam, let's say you have a cube like that. Okay, and you want to calculate some divergence of let's say this quantity, divergence of u, for example. Okay, so this is the divergence of velocity. Hopefully you know what that is. So this is over the whole control volume. So divergence of velocity is the net, it is a net outflow of velocity. So remember, divergence is the del x, del y, del z. Hopefully you have done your fluid mechanics, you are familiar with this term because it will pop up a lot in the Navier-Stokes equations. So this is the divergence term, and what it is that, okay, the other way of writing this is to have this surface integral. Okay, so you see this thing here is actually called the surface integral. Okay, so I'll go back here. This will be the surface integral of n dot u dA. So what is this saying? It's saying that, okay, if I integrate the divergence over all the volume here, it is the sum of the flux, the net flux actually entering in and exiting. Okay, you have to sum up the flow, for example, of u. You have to sum up the flow of u through every single surface, right? So another way of, so divergence, if you integrate it across the whole volume, it means that you have to sum up the fluxes of the said whatever you're diverging across all the surfaces. So for so that's a pretty simple thing, right? So basically both of these are talking about the same physical thing. It is the net inflow or outflow. Yeah, this is talking about net outflow. Yeah, net outflow of, let's say, some quantity like velocity. So to integrate the divergence across this volume, you need to do a surface integral, meaning to say you have to check the inflow and outflow at each of the surfaces of this said cube or this hexahedral. So this is called Gauss Theorem. This is a very, very brief run through. I hope you are familiar with it. Okay, so how is this surface integral calculator in OpenFoam? Basically, I have to sum from I equals to 1 to 6, since this is a hexahedral cube, or I can put n cubes, right? So I have the area. So I have the area of this, right? And of course there's a dot product here, so if this is a vector especially, so I have a cosine theta between the u and the normal to the area, and of course we have u at the face. So let's say between these two faces, the u is here, the u is coming this way, the normal is going this way, you'll have theta here, and this is the area dA of one phase. So let's say this is the first phase, and this is the relevant velocity coming in. I'll have to do a cosine theta and multiply into the area of this phase, and then I have to repeat the summation across all 6 phases, right? So A1 U1 cosine theta 1, A1 U2 cosine theta 2, blah blah blah, across all the phases. Okay, so this is the long and short of how OpenFoam does Gauss Theorem integration, so that you know, we have our results. Now, the tricky thing about this is how it is being done, especially when the phases are not so straightforward. They are not so nicely put together, because okay, let's say we have this. Let's say we have a very nice mesh like this. You have a U at this cell, and then this is U2, all right? U1 and U2, correct? Okay, so we want to evaluate, let's say, the flux going from the cell 1 to cell 2, right? So we have some value for U inside this cell. Let's say this one's going this way, this one is going this way, right? So how then do we evaluate the U here? Okay, so this is the U at the face, which is what we are interested in. We know the area of the face. We need to know the U of the face. So how is the U of the face being determined? So one simple way is to do a linear interpolation between these two U's. So for example, if we have this x here, there's a distance x or delta x, right? U phase can be equal to this gradient, or this U1 plus, okay, delta U, delta x, U2 minus U1 over delta x. And then we multiply by the distance here. Let's say this is x1, okay? So x1 is here. This is called, of course, linear interpolation. If your mesh is very nice, this thing works nicely. So you'll have some representative some representative velocity here. Okay, so we can just by inspecting these two arrows, we can actually guess what this velocity here will look like. Yeah, we can guess what the velocity there will look like. Now, problem is for a very awkward mesh. Let's say you have very funny shapes like this. U1 and U2. Okay. Now you have a very awkward mesh like this, and then you try and interpolate this phase velocity, at this phase, by using the same method. Okay, this is called the linear method, right? Linear. This is using linear interpolation. But if you use the same linear interpolation here, does it work? The answer, of course, is no. There will always be some error. So what you're actually interpolating is the velocity here. You interpolate it. So this is U interpolated but the U phase is not equals to the U interpolated. Okay, the U phase here, it is not equals to the U interpolated. And let me circle that up so that it's less confusing. So U interpolated is not equals to the U phase, and this is one source where the error can start propagating out of control like crazy. So there are a few ways we can play around with fvSchemes to solve this problem. But if your mesh is so bad, then this thing can actually spiral out of control and possibly lead to other problems in the flow, the stability of the flow, or the stability of the solution. So this little error here, that could be a very important reason why we see the temperatures fluctuating like crazy just now, and that is due to a bad mesh. Okay, so that was the learning point from a lot of experiments I've done, and yeah, so this is what I was trying to explain to myself. I mean, document down what was going on, and that was what I presented to you just now, that the very awkward shape of the mesh is going to give you very, very funny results. Okay, so I'll stop the video here and I'll continue discussion in the next video.